Okay, so the next type of metamorphism, we move from contact metamorphism to the next type, which is regional metamorphism. As I mentioned before, there are different types of regional metamorphism because this is just based on the area that the metamorphism basically affected. But in this particular case, gagamitin natin yung regional metamorphism in the context of orogenic metamorphism. So orogenic metamorphism is when we have mountain building processes, either through due to basically convergence between plates. So we experience or we see this type of metamorphism when we have arc ocean oceanic collisions, continental convergence, or arc continent collision zones. All these are part of or of the rocks. In these cases, usually experience orogenic metamorphism. So this happens when we have convergent plate margins. This is also known as dynamothermal type of metamorphism. Dynamo or dynamic, referring to the differential stress, and thermal representing heat that is usually caused by either the underplating of basaltic melts, for example, in arcs, or the rise in geothermal gradients due to or the elevated geothermal gradients produced by collision, which results to crustal shortening. So these events or this orogenic metamorphism usually involves multiple deformation events with elevation of temperature resulting to the foliated nature of the metamorphic rocks, typically comprising these tectonic terrains. So let's keep first yung subduction. We can first think of or yung continent-continent collision. For now, continent collision usually starts as a subduction. For example, an oceanic continent convergence, which we refer to as the Cordillera type of subduction, or the Tethyan type subduction, which is oceanic convergence. So shown here, for example, is an example of Cordillera type subduction, wherein we have this oceanic slab subducting beneath this continental crust. And here we also see the development of what we referred to as before this lecture 2, yung paired metamorphic belts natin. So as I mentioned before, yung high pressure, low temperature represents yung subduction interface itself. So these rocks experience very high pressures, very high degrees of differential stress. But the temperature here is depressed. It's not elevated because of the basically warping ng ating geothermal gradient. On the other hand, dun sa likod ng arc, dun sa likod ng subduction rather, sa likod ng subduction, sa base ng arc, so what we see here is the underplating of basaltic magmas as a product of the subduction process, as well as the crustal shortening, which also elevates yung ating, which can also elevate yung ating geothermal gradients. So kung dito, depressed yung geothermal gradients because of the plate flexure, yung flex ng plate natin due to subduction. Dito naman, dahil sa pag-akyat ng crust natin due to crustal shortening, na-impit siya, tumataas din yung ating, na-elevate din yung ating geothermal gradients. And that elevated geothermal gradients, together with the underplated magmas, can result to low pressure but higher temperature metamorphic rocks in the surrounding area. So, yun yung paired metamorphic belts natin. So let's see just a quick review of subduction initiation in Tethyan type naman setting. So when we have Tethyan type subduction initiation, we usually have this low PT, low to moderate PT gradients. So when we say low P over PT, that means low pressure, high temperature. So this, aside from the discussion a while ago that we also see this geothermal gradient kapag ka nandun ka sa likod ng arc. Yan, pag nandito ka sa arc mismo. We also see this kapag meron kang oceanic subduction initiation. So oceanic crusts in general are much thinner and much warmer. Yung geothermal gradients nila are much warmer than continental crust. And therefore, when they start to collide and subduction is initiated, usually the base of that subduction zone, basically ito, yung interface ng subduction zone na yun, experiences much elevated or much higher temperatures compared kapag compared when the subduction matures. So as the subduction progresses, basically, sige, ito muna. Let's think first of a spreading center. Kasi that's one way of, or that's one region uh, where where oceanic convergence starts. So that's one way because spreading ridges are basically areas of or weak plains. And if we push basically the oceanic fragments together instead of divergent stress, we compress them. Subduction may be initiated along this um, spreading center. So when that happens, what we have here is a very warm mantle material. And as this slab here goes beneath the other slab, it interacts with that very hot mantle material. So very hot mantle material, pero the pressure is not too much, not so much, kasi the overlying slab is not that thick since it's oceanic. So that results to usually low PT metamorphism. And for example, these rocks at the base or at these rocks at the top rather, at the top of the subducting slab may sometimes be preserved beneath this oceanic fragment on the overlying oceanic fragment, which we refer to this part, we refer to these metamorphosed units as the metamorphic zone of this oceanic crust or oceanic lithosphere rather. So oceanic lithosphere. So itong metamorphic soul na to, for example, in Oman and other ophiolitic and ophiolite units, usually they represent or they preserve low pressure, high temperature gradients. So like this. As subduction progresses, basically the fluids trapped in this subducting slab gets liberated, as we mentioned before. Kapag may subduction ka, one effect is devolatilization. So since they experience hotter and hotter conditions, deeper and deeper at deeper and deeper depths, they start to devolatilize, and those fluids actually cools the mantle so that as you progress from young subduction, from subduction initiation into mature subduction zones, what we see is the cooling nitong interface. So from low PT into something more high PT. So ito yung high P, low T terrains na characteristic of mature subduction zones. So this also introduces yung facies series natin, or also known as the baric types. Baric meaning pressure types. So low pressure, moderate pressure, and high pressure. Low pressure is usually reserved for or only seen in shallow intrusions. But as we've discussed before, pwede rin siyang makita in subduction initiation, in particular Tethyan type subduction initiation, usually preserved as metamorphic zones. High PT, moderate PT rather, moderate PT is usually observed in deeper subduction zones rather, not deeper subduction zones, but deeper intrusions. So when we think of magma chambers, for example, of island arcs, of more mature arcs. So yung magma chamber nila is located somewhat deeper, so hindi na siya shallow intrusion. So it experiences the same amount of temperature, the same very high temperatures, but at more higher pressure compared to shallow intrusions. Then high PT, this is usually only seen in subduction zones along the subduction interface to be exact. Okay? Yeah. So yun yung different facies series. So for example, when we say moderate PT facies series, we usually see rocks of this metamorphic uh, grades. Green schist, followed by epidote amphibolite, followed by high pressure amphibolite, followed by granule. Compared kapag meron kang shallow intrusion, what you usually see are the hornfels, the different types of hornfels, followed by sanidinite. If you have high PT facies series or high PT barric type, then you only expect or we typically only find blue schists and eclogites. So yun yung concept diba, ng facies series natin. An example of a moderate PT type facies series or moderate barric type is the Barrovian zones. So yung Barrovian zones represents a medyo deeply buried na or deep intrusion. So the pressure is a bit high and the temperature was quite high. So this Barrovian zones are exposed in the Scottish Highlands. It shows variations in rock types with metamorphic grade folding and granite intrusions related to Cordilleran type of subduction. So kaya rin siya medyo deep-seated na intrusion kasi the arc developed in a continental crust. Yeah. So, and also, please take note that the Barrovian zones, the mineral isograds reflected here are that of metapelitic rocks. So, hindi siya yung kanina na green schist, blue schist, and green schist, and then epidote amphibolite, and then granulite. Of course, they are equivalents, but instead of the metamorphic grades na based on mafic rocks, as we can see from here, these zones are based on index minerals typically found in metamorphosed pelitic rocks, so mudstones, shales. Yeah. So, but the same is true. So, in terms of mineralogy, it also changes depending on the temperature. So metamorphic zones are based on the appearance of a new mineral as the metamorphic grade increases, as temperature increases. So usually the lowest grade or the lowest grade metamorphic rocks in these zones are the chlorite zone, followed by the biotite zone, garnet zone, staurolite zone, kyanite zone, and then sillimanite zone. Hindi ko na siya masyadong i-discuss, but these are the details of the different minerals that we can see in these different zones. So I think yung highlight lang naman dito is that very much like a mafic rock actually. So if you remember yung green schist facies, lowest grades, we also see chlorite plus a low andesite plagioclase, albite. And then as we go up up the grade towards increasing metamorphic grade, we now see less we now see biotite coexisting with chloride, still with albite. And then as you go further, this hydrous minerals becomes unstable. Chloride, to be exact, starts to break down to form garnet, and albite starts to break down to form oligoplates. And yeah, and then this muscovite starts also to break down another hydrous mineral starts to break down papunta sa ating staurolite zone. So eventually the chlorite and muscovite grains and the albite, basically they start to break down to form less hydrous aluminosilicates like staurolite, garnet, and plagioclase. And then eventually from staurolite zone, we basically further break down yung muscovite until eventually you have saturation of aluminum in the system so that it forms aluminosilicates like kyanite. And then if we further increase the temperature, this kyanite can transition into sillimanite. So it's important here to note the transition. It's from kyanite to sillimanite. From here, ito is already a marker or an indication na this is at least moderate P over T. Kasi kung low P over T to, the aluminosilicate that would have been formed would be andalusite. So, sana nai-imagine nyo na ngayon kung nasan yung andalusite, highlighted sa diagram, sa PT diagram. So, take note, however, na itong isograds na to, itong first appearance ng minerals na to is not constant, is not true for all pelitic rocks. So as mentioned before, some of the more common pelitic rocks actually has another zone referred to as the chloritoid zone, so chloritoid in zone. And the location of this, the P pressure and temperature conditions by which or by at which point supposedly nagbabago-bago from garnet to staurolite to kyanite, hindi rin siya fixed sa PT space. It all depends on the bulk composition which affects yung presence or absence nitong assemblages na to and the location when or the timing when in the PT space this transitions will begin. So that's always important. When we talk of transitions, it's always about the pressure, the temperature, and the bulk composition of the protein. Yeah. So, na-mention ko before, yung paired metamorphic belts. So, yung kanina, this is yung Barovian series. Ito yung nag-represent ng arc, essentially, yung island arc or continental arc natin. Whereas yung itong blue schists, eclogites, o kaya sa case ng young subduction, yung metamorphic zone naman natin, they represent the subducting slab. So this pair is usually what we refer to as the paired metamorphic belts, which are markers of subduction zones. Again, the high P, low T represents the four arc or trench lithologies, while the low P, high T lithologies represents the main arc granulite. So for example, this was first recognized by Miyashiro in Japan when he identified yung Sanbagawa metamorphic belt as the high P, low T rocks. They are composed mostly of blue schists and some eclogites. And then behind that is the Ryoke Abukuma metamorphic belt. You may also be familiar with this Ryoke Abukuma metamorphic belt because it's a good alternative for this Barovian series. A good alternative kasi it is actually more complete in terms of the zonation. So meron siya ng chloritoid zone compared dito sa Sambagawa na na kulang-kulang minsan isograds. Although, mas familiar tayo sa sa Barovian series kasi ito yung mas widely publicized. Okay? But anyway, they represent the same thing. The Barovian series and the Ryoke Abukuma metamorphic belts represent the arc, whereas yung Sambagawa represent yung subduction zone. Subduction interface. Okay. So question, which environment would you expect metamorphic rocks with blank as the dominant minerals? With A, chlorite and actinolite, ano kaya siya? Sa zone 1, zone 2, zone 3, etc. So, o kaya yung opposite and garnet. How about orthopyroxene and andesite? So first, chlorite and actinolite. This is basically green schist facies, diba? So green schist facies, ang kaya siya may expect? Green schist facies has to be not that high temperature. Pressure must be a bit, nandun na rin, some intermediate pressure. So you might think of maybe number 5, for example, or even number 6. Yeah. How about omphacite and garnet? Omphacite and garnet is a eclogite, basically, diba? The key minerals for an eclogite. And if you have an eclogite, it requires high temperatures and high pressure. High temperature like 4 and high pressures like 4. Yeah. How about orthopyroxene and andesite? This requires moderate amounts lang ng pressure. Hindi pwedeng too high kasi pag too high yung pressure, magiging eclogite siya. Pero the temperature must be high. So temperature must be high, so you can think of maybe number 8. So, yeah. Okay, so yan yung mga zones. Tingnan natin. So 4 is eclogite, tama yung example B. Yung 5 is yung green schist, yeah. And then yung 8 yung granulite. Yeah. Okay. So, this is just side info. As I've mentioned before, paired metamorphic belts or even the locations of high P over low P rocks indicates subduction zones, ancient and active subduction zones. And as you can see, this is a global distribution of blue schists and eclogites. And the interesting point here is that when we look at this map, we know that the Philippines has been an active zone of collision, of convergence for the past 50 million years at least. But as you can see from here, walang ni isa pang reported na blue schist and eclogite locality sa Pilipinas na well documented. So wala tayong representation dito. Bakit kaya? This does not mean, of course, na walang subduction sa Pilipinas ever since we do know that there is. It's just that hindi kulang pa sa pag-aaral yung blue schist and or yung metamorphic rocks in general dito sa Pilipinas. So that's a challenge for us. We have to find these ethologies, and this, as we've seen before, these ethologies are actually very good markers for ancient collision zones or ancient subduction zones. Yeah. Another type of regional metamorphism is static or burial metamorphism. This is the type of metamorphism, static or lithostatic metamorphism or burial metamorphism. This happens when you have massive amounts of material accumulating in a subsiding basin, usually in a four-arc like this, in a four-arc setting, or pwede rin sa passive margins dun sa passive margins. Makapal, pwede rin makapal yung sediments mo. And the thick sediments is due to the previously divergent nature ng boundary, ng margin. So usually, this only results to low-grade metamorphism in the deepest layers only, with no significant deformation. For example, gaano ka lalim before mag-metamorphose? Usually, for an example is the Bengal fan. So Bengal sa India, yung Indian, yung Bengal River nagde-drain dito papunta sa Bengal fan. Basically, 22-kilometer thick sedimentary pile only resulted to 250 to 300 degrees Celsius with pressures of up to 6 kilobars. So very low grade, less than grain schist species pa nga ito. And therefore, we only expect, or the highest grades, we usually expect just clay minerals, prehnite, pompillet, and some clay recrystallizing to, for example, lomantine. So very low grade metamorphism. And another low grade in the sense that in terms of temperature, it's not really high temperature that much. So ocean floor metamorphism, but in terms of area, since it's widespread, it's regional metamorphism. So you can think of it also as hydrothermal because it involves, of course, seawater percolating or circulating, coming down from these fractures and circulating, getting heated up by this magma and then circulating to the surface, affecting yung rocks, maybe adding some components into the rocks and taking out others. So yun yung action ng hydrothermal metamorphism / metasomatism. So this happens when you have hot iron-rich fluids circulating through fissures and cracks in rocks associated with spreading centers. We know it's not only in spreading centers, ito lang yung regional in scale kasi lahat ng ocean floor technically, lahat ng oceanic crustal material, especially yung pillow lavas or yung volcanic section and even gabbroic section, yun typically yung nakakaranas nitong ocean floor metamorphism. So lahat yun ay affected, or most of it ay affected nitong type ng metamorphism na to kaya regional in scale. However, this same process of hydrothermal fluids interacting with molten material and basically affecting yung chemistry ng surrounding rocks is also observed in smaller scale, and we refer to that as simply hydrothermal metamorphism. So for example, beneath geothermal power plants, beneath ancient volcanoes, which are now preserved as hydrothermal deposits, porphyry copper, Epithermal gold systems, these are basically solidified versions nitong hydrothermal metamorphism process. Yeah, so ito yung some examples of ocean floor metamorphism. These are pillow lavas. Basically, kita pa yung pillow structure nila. Pero we can see the discoloration of the core, which is more yellow compared to the rim, which is more red. And the reason for that is the core is now more epidotized. So, nadagdagan siya ng calcium. Whereas the rim is more chloritized. So, nadagdagan siya ng magnesium. Yeah. So, chloride-rich yung rim natin, higher magnesium. Epidot is, whereas yung core is more rich in epidot. Yeah. So we also see the same thing. So ito pala yung tsura ng calcite, ng chloride sa PPL. So we have this greenish material, the calcite in the interstices, nitong vesicles, basically. Yeah. So in this particular case, in this particular locality, na ka-experience ng up to amphibolite facies na metamorphic grade, yung pillow lavas. Where in some localities, it's usually green schist species only. Yeah. So at smaller scales, beneath yung systems na meron ka pa rin circulating fluids and usually a heat source rather. You have a heat source, you usually form also hydrothermal metamorphism, or you also the rocks will also experience hydrothermal metamorphism. This may be preserved as veins, especially along tension in shallower regions kapag may tensional stress ka, which can then form these open fissures to be filled up by these fluids, which can be filled up by these fluids, resulting to these structures, so these vein structures. And if you have deformation like this, for example, so if you have a shear stress, hindi naman siya necessarily tensional stress na pull apart. Basically, pwede siya actually shear stress. But as a function of the shear stress, you can form these tension structures. So open fractures. Okay, so ganito yung itsura niya. And as you may notice, the mineralogy of these veins actually reflect the chemistry of the fluids that pass through them. So this one, for example, is composed only of quartz and some hornblende. So that reflects kung ano yung chemistry ng fluids na pumasok sa kanya. These are mostly rhodochrosite, zeolite crystals, needle-shaped zeolite crystals. So that's also a different type of fluid. C, this is feldspathic. These are quartz veins cutting through feldspathic units. So these are the tension cracks that we've seen before. And then D is feldspar, epidote. Feldspar is in pink, epidote yung green, and then garnet yung mga red, pinkish na minerals na top. So this represents, if you know the chemistry of, or if you know the chemistry of these minerals, itong vein na to represents a fluid which must have included or which must have been transporting aluminum kasi epidote and alkali feldspar as well as yung garnet all require aluminum para ma-form siya. Must have also contained some potassium para maka-form alkali feldspar and some calcium para mag-form ng garnet and ng epidote. So, yun. Kung ito, SiO2 lang basically yung composition ng fluid, this one is definitely more complex. Some of this may actually not even be a simple fluid. It may actually be basically a melt na, lalo na it's transporting components that are supposedly fluid immobile like aluminum. Yeah, ito naman, this is an interesting vein wherein you have your core, which is just quartz, and yung rim, which is diopside. This could indicate a change in the chemistry of the fluids from something that contains calcium and magnesium to something that's purely SiO2. And so those kind of information yung makakuha natin sa veins. Yeah, and then We also have, of course, fault zone and impact metamorphism. So ito na yung medyo hindi na to regional in scale. Ito na yung last type of metamorphism. So this usually happens when you have high rates of deformation with minor thermal recrystallization. The minor thermal recrystallization is important for you to preserve yung cataclastic na texture or na fabric nitong rocks na to affected by fault zone and impact metamorphism. Okay? Kasi pag nire-crystallize na siya, it becomes coarser, hindi na siya cataclasis. So, cataclastic rather. So, cataclasis usually represents the minerals that are broken, bent, or crushed without accompanying recrystallization. So, ano ba masasabi ko? Usually, this type of rocks, as we will see later, is reserved to shear deformed rocks. So sheared rocks. This is a shear stress rather. Shear stress is of course a type of differential stress, but it produces a different type of fabric compared to compressional or tensional stress. Okay? Kaya again, itong cataclastic texture, itong naming na to na makikita natin is reserved for shear stress. For rocks which experience shear stress only. Yeah. So usually these are preserved sa shallower surfaces as fault breccias or fault gouges. Gouges kapag clayey, breccia kapag breccia pa parang ganito, malalaki pa yung class surrounded by a ground up matrix. And at shallower depths, this of course transitions to more ductile deformation. So you end up with myelinite, different types of myelinite, ultramyelinite, paramyelinite, marking ductile deformation. Okay. Yeah, so these are some examples. This is a breccia. Here you can see this fold, which indicates shearing. This is a pseudotachylite, itong glassy material na to. Pseudotachylite, pseudo, it's like, literally means is like. And then tachylite is glass, so it's like glass kasi basically due to shearing, the rocks at depth can behave like a melt, pero they are actually very fine-grained, ground-up version surrounding rock. And we see also here this sigmoidal quartz grains, which represent shearing in this manner, and this porphyroclasts surrounding by this fine-grained matrix. Yeah. So when we talk of fault zone or dynamic metamorphism, blast or blastic refers to a feature that is metamorphic in origin. Usually, pag sinabi natin blast or blastic, newly grown texture or newly grown mineral siya. So porphyroblast is a newly grown mineral. Kapag for example, clastic naman, or porphyroclast or porphyroclastic texture, you have an old material that's been deformed or ground up so that yung surrounding matrix has the same composition actually as the coarser material. So yun yung difference, di ba, na blast or blastic, tsaka clast and plastic. Okay? So, both are metamorphic in origin, pero, hindi sila inherited from the protolith, but one represents yung blast and plastic represents new growth, whereas clast or plastic represents deformation of the old material into something more fragmented version. Important na it's metamorphic in origin kasi kung if it's from the protolith, then that's what we refer to as the relic structures. The relic structures are structures that are inherited from the protolith, for example, relic bedding and relic igneous minerals. Relic with a T, not relic na R-E-L-I-C lang kasi relic na R-E-L-I-C ay religious materials. Okay? And then other terms to be defined, idioblastic, hypidioblastic, and xenoblastic. Idio, this basically means euhedral, subhedral, and unhedral respectively. The grain sizes suggested by the IUGS SEMR, so parang igneous rocks lang, so ultra fine grain 0.01, very fine grain 0.1, fine grain 1, and medium grain 4 millimeters, coarse grain 16 millimeters, and very coarse grain more than 16 millimeters. So, dynamic metamorphism some textures related to dynamic metamorphism. So deformation mechanisms in order of decreasing temperature and or strain and decreasing strain rate. So yung least amount of stress basically is what we call or usually produces cataclastic flow and solution transfer. Cataclastic flow is when you have mechanical fragmentation and sliding and rotation of fragments. So basically, hindi pa siya nagduro. Nagro-rotate lang yung grain natin. So that's cataclastic flow. And in some cases, kapag mayroon kang pressure that is like this, not only is shear, okay? Not only shear, pwede siyang all types of differential stress. Hindi pala all types. Yung compression o kaya shear. So both types, the rocks, under both types, the rocks will experience complete or partial compression. Partial kapag shear. So partial compression and along the grain boundaries kung saan kung nasan yung stress, the material may start dissolving and itong dissolved material may be transported by the intergranular fluids and transferred to the sides where pressure is less, where stress is less, so that in the end what you have are these pressure shadows. So for example, here you can see this elongate quartz grains like this one. And then when we look at the timing of growth nitong quartz grains na to, which you can do using compositional mapping. In this case, I think they did cathodoluminescence mapping. You can see basically that this was the original quartz. And then you have these newly grown quartz subgrains. Na itong subgrains na to represents yung dissolved material and reprecipitated materials dun sa sides with least stress. Kung yung compression is this way, kaya ganyan yung foliation. So that is what we refer to as solution transfer or pressure solution. So this happens when you have flattening occurring in rocks with rigid grains. The crystals can precipitate on the sides of the crystal. So we refer to this as pressure shadows. So ito, for example, you have your garnet grains, quartz along the foliation or parallel to the foliation. Since na-compress sila to the side, yung quartz, some of the quartz in the matrix started to dissolve and then was transferred dito sa region na to, pressure shadows, kung saan less yung stress dito sa ating surroundings sa ating garnet. Okay? We also see that here. This is, I think, another garnet grain. And again, we see this quartz overgrowth here. But what's interesting here is that, so ito yung garnet, same quartz. What's interesting here is that hindi lang yung quartz actually nagdi-dissolve. As you can see from here, sa close-up, we see this overgrowth din. And I think this is, a biotite. So you see this overgrowth din sa biotite. Yan, itong very non-foliated na natin. So these are basically newly growths. So hindi na siya newly grown crystal subgrains formed as a product of the compression dito. Yeah, yung vertical compression. Yeah. Okay. If we further increase the deformation and we decrease yung temperature for crystallization, what we have is basically a shredded appearance and angelus extinction, ubiquitous within the rock. And eventually we end up with porphyroclasts surrounded by a matrix that is fine-grained. So this ground down material, which was basically derived from the porphyroclasts, this texture is what we refer to as the mortar texture. So the clasts are remnants of broken, larger, pre-deformational grains, and the larger grains are referred to as porphyroclasts, and the surrounding material are referred to as the matrix. And itong texture na to, we refer to that as mortar texture. So ito yung least amount pa ng shear stress. And then as you go further, it becomes smaller and smaller till you end up with this mortar texture till eventually, if you further stress them out, pwede wala na talaga porphyroblast. Ito na yung ultramilonite. So ultramilonite represents very fine-grained rocks which are actually the product of extreme grounding, essentially. So ganito, for example, you have here this porphyroclastic tectonites, porphyroclastic peridotites, basically. Yeah. And then, start ng deformation, ng shearing rather, you develop them further into proto-myelonites like this, and then myelonites like this, and then if you further ground this up, this will become ultramyelonite, very fine grain. Okay? Yeah. So, and in rocks of lower temperature, pseudotactylite can form, representing localized rapid fragmentation and melting due to shear heating. So, kaya siya able to flow and be like this. Yeah. This shearing can also form in rocks yung tinatawag nating SC planes or SC structure, where S represents the schistosity. So this is actually the schistosity foliation surface. Schistosity is similar with another foliation. So schistosity or foliation surfaces is like this. And then the C planes represent the xylaman. This is French word. Forgot how we, yeah. Anyway, foliation, this is another foliation separating these S planes. So these C planes actually represent shear planes, yan, accommodating yung shearing nitong unit natin. So you have this, you end up with this wavy pattern. So S is the direction of elongation to the shearing, while C is the spaced cleavage transecting well-developed simultaneous mineral foliation. So SC fabrics are very nice indicators ng shear direction. So in this particular case, left lateral. But other markers such as porphyroblasts, na may shadowed porphyroblasts like this, or shadowed porphyroblasts rather, like this sigma type or delta type. This is actually sigma or phi type. These two were not actually very good markers for shearing. They indicate lang na may compression ka this way, kaya may compression shadows in gray sides. Delta type and sigma type, delta type and omega type. Yun yung mas yung tails nila, if you can identify them properly, they can tell the shear direction. The same yung comment before. This type of textures, you should only observe this dun sa plane. Sa plane parallel to the foliation plane. So essentially yung foliation planes. Kapag may nakita kang delta type porphyroclast dun sa foliation plane, then that tells you where the stretching is happening. Okay? Stretching is happening, meaning sigma 3 is there, parallel to that direction. So, dun mo naman sabi. So, yun. Hindi ka pwede mag-identify perpendicular to the foliation plane. Dapat along the foliation. Para foliation plane is dapat nandun yung shear stress indicators. Okay? Then you can also have quarter folds like this. You can interpret like this. Meron din yung quarter mats, asymmetric folds like this. And basically this is a translation of here. So meron kang compression sa side na to, kaya may folds. And then meron kang extension on quadrants 2 and 4, kaya meron kang buttons on quadrants 2 and 4. Okay? Some fault zone photomicrographs. So you see here this cataclastic textures, these protomyelonite textures, protomyelonite meaning, ano pala yan siya? Yung how you identify if it's already protomyelonite, myelonite, ultramyelonite, it's depending on the dominant grain size. So kunwari ito, 10% of the grain size have been reduced into finer matrix, so kaya siya protomyelonite. Ultramyelonite is 90 to 100% fine materials naman siya. So, ganyan siya. And then E to F is, this is just myelonite path. Okay, and ultramyelonite na G to F. voltage. Yeah. So next next concept